Alright, welcome to the second video of unit number 6 where we're going to talk about power. Now power is related to work as power is the rate of doing work on an object. You'll also see there that it says or changing energy, so it could be the rate of doing work or the rate of changing the energy of an object. It could be either or. We'll see why that's true in a second when we get to the work and energy relationship. But that gives us an equation as the rate of doing work, which is work divided by time, gives us power. So this is power, and this is work, and this is time. Now the units, if we think about work, we had newtons times meters. We're dividing that by time, which is in seconds, so we get newtons over meters in seconds, which is equivalent, because a newton meter was a joule, which is the same as a joule over second, which is given the name of a watt, which is a capital W. Now you have to make sure that you don't confuse the work capital W, which is the symbol of work, and the unit of power, which is a capital W watt. Make sure you can keep those two different, and that's where it's important to write out things properly. So let's take a look at an example. An electric motor lifts an elevator 9.00 meters in 15.0 seconds by exerting an upward force of 1.20 times 10 to the 4 newtons. What power does the motor produce in kilowatts? So we have to always go to your equations and see where they lead you. So if power is what we're looking for, we know the power equation is work over time. Well, work is not in our list of givens, so if we know what work is, which is force times its distance, and we get over time. So F times D over time. Now we have F, we have D, and we have T, so we have everything we need. What you have to make sure, though, is that if you're doing work, are the directions that the force is applied and the object is moving the same? And if we're exerting an upward force and moving an elevator upwards, then yes, they are in the same direction, so the work is done. And we can just calculate ahead as normal. So we get 1.20 times 10 to the 4 newtons times 9.00 meters all over 15.0 seconds, which gives us 7,200 watts. Now you have to be careful. This question does specify to answer in kilowatts. And to proper sig figs, it's going to be 7.20 because it's 3 sig figs kilowatts. Always make sure you're answering questions as they're asked. So work and energy. So if you lift a box, you've done work because you've lifted it up, you've moved it some distance and by applying a force. So you've done some work, but you also, if you think about how bodies work, you've used some energy. But the energy can't go it has to go somewhere, and we'll see why that is when we get to conservation of energy a little bit later. And then, so it goes to the box somehow. So the box has gained energy if you've lost your energy. So it has the ability to do work if we dropped it, which we'll see where that relationship connects to energy later as well. So what is the connection between work and energy that we're looking for? That if we do work, we've changed its energy. So we can write that exactly as it sounds as an equation. If work is done, it is equal to our change in energy. So that's a very important idea, and that allows us to do a couple of different things. So if we think about our equations, we've got the work is force times distance, and we've got the power is work over time. You know, we can change things up. We can say that power is also the change in energy over time, or power is force times distance over time. Or we could say that the change in energy is F times D. So there's lots of different ways that we can combine these couple of equations to solve given the variables that we have. And that's always an important thing to think about. So you write out your givens, start with your equations and see where it leads you, and hopefully you'll get to an answer. So try out those practice problems there, and as always, physics is awesome.